It is the summer of 1867. An Austrian physicist named Ludwig Boltzmann is 23 years old and working in Vienna, and he has just started pulling on a thread that is about to unravel something enormous. He is trying to understand why heat moves the way it does. Not the broad brushstroke version. Everyone understands that hot things cool down and cold things warm up, that a fire eventually goes cold and a block of ice eventually melts. What Boltzmann wants to understand is why, the deep mechanical reason, the thing underneath the thing. He spends the next decade following the mathematics wherever it leads. The answer he finds is simple to state and almost impossibly far-reaching in its consequences. He finds that the universe is not indifferent between order and chaos. It is biased, systematically, irreversibly, structurally biased toward disorder. Not because of any force pushing it there. Not because chaos is more attractive or more stable in any physical sense. Simply because there are far more ways for things to be disordered than there are for them to be ordered, and given any opportunity to change, the universe overwhelmingly tends toward the configuration that has the most options. Boltzmann calls this entropy. And what he discovers is that the universe's preference for chaos is not a tendency or a rule of thumb. It is a law. The second law of thermodynamics. A law so foundational that it governs everything from the cooling of your coffee, to the death of stars, to the ultimate fate of the cosmos. The implications will take a century to fully absorb. Some of them we are still absorbing. And the deepest implication of all, the one that sits at the bottom of this whole story like a stone nobody wanted to pick up, is that everything you have ever seen, everything you have ever touched, every structure and pattern and living thing in the observable universe exists in defiance of what the universe prefers. You are a pocket of order in a universe that would very much prefer you not to exist. Not maliciously, just statistically, overwhelmingly, inevitably, statistically. This is the story of that preference, where it comes from, what it means, why it is both the most certain law in physics and the source of the deepest unsolved questions in all of science. Before we go any further, right now, wherever you are watching this, I want you to look around and drop something in the comments. Tell me whether the space you are in is tidy or messy, organized or cluttered, everything in its place, or in a state that your mother would not approve of. Because what you are about to learn will completely change the way you think about that question. And if this is your first time here, welcome, subscribe, and get comfortable. We are about to follow entropy from Boltzmann's desk in Vienna all the way to the heat death of the universe, and discover that the universe's preference for chaos is simultaneously the reason everything falls apart and the reason anything interesting ever existed in the first place. The law nobody can break. Start with something simple. You have a cup of hot coffee sitting on a desk in a cool room. You leave it there. You come back an hour later and the coffee is cold. The heat has dispersed into the surrounding air. The room has warmed very slightly. The coffee has cooled significantly, and everything has approached the same temperature. This never happens the other way around. You never come back to find the coffee hotter than you left it, with the surrounding room slightly cooler. The heat never spontaneously flows back from the room into the cup. In 100 years of watching coffee cool, in 1 trillion experiments in thermodynamics laboratories around the world, Nobody has ever seen heat flow from a cooler object to a warmer one without external intervention. Why not? It is not because of any conservation law. Energy would be perfectly conserved if heat flowed backward from the room into the cup. The first law of thermodynamics, conservation of energy, would not be violated. The total energy of the room plus coffee system would remain identical before and after. There is no bookkeeping reason why the reverse process cannot happen, and yet it never does. The reason is the second law of thermodynamics. In any closed system, the total entropy either stays the same or increases. It never spontaneously decreases. Entropy, in Boltzmann's formulation, is a measure of the number of ways a system can be arranged at the microscopic level while still looking the same at the macroscopic level. A cup of hot coffee in a cool room has a relatively specific, relatively constrained microscopic arrangement. The fast-moving molecules are concentrated in the cup, the slower ones distributed through the air. There are relatively fewer ways to produce this state. A cup of coffee and room that are both at the same temperature has an incomparably larger number of possible microscopic arrangements. Any of countless quadrillions of configurations of molecular positions and velocities would produce the same macroscopic appearance. The second law in Boltzmann's interpretation is a statistical law. The universe tends toward higher entropy, not because it is pushed there by any force, but because higher entropy states are vastly more probable than lower entropy states. When molecules in a system are free to move around and exchange energy, they will, with overwhelming statistical certainty, find themselves in one of the enormously numerous high-entropy configurations rather than one of the very rare low-entropy ones. It is not that the universe prefers disorder in any deliberate sense. It is that disorder has far more addresses, and random motion almost inevitably ends up at an address that belongs to disorder. Here is the number that makes this concrete. The entropy formula Boltzmann derived, S equals K, times the logarithm of W, where K is now called Boltzmann's constant and W is the number of microscopic configurations, is one of the most powerful equations in the history of physics. It is engraved on his tombstone in Vienna, which is either a beautiful tribute or the most appropriate epitaph ever written, depending on your sense of humor. The equation reveals something extraordinary. The difference in the number of microscopic configurations between a disordered state and an ordered state is not large. It is not very large. It is not astronomically large. It is a number that makes astronomically large look like a rounding error. When you calculate W for a cup of coffee versus a cup of coffee and room at equilibrium, the ratio is something like 10 to the power of 10 to the power of 23. A 10 followed by 100 billion trillion zeros. Not a number, not a quantity that has any intuitive meaning. Simply proof that the ordered state is so improbable that calling it unlikely is a laughable understatement. The second law is not an approximation. It is as close to absolute as physics gets. What entropy is not? Before going further, it is worth addressing a common confusion that does real damage to understanding this subject. Entropy is not messiness, not exactly, not in the simple visual sense. A tidy room is not necessarily low entropy. A messy room is not necessarily high entropy. What matters is not how things look, but how many microscopic configurations could produce the same macroscopic appearance. Consider a glass of water. Every water molecule is bouncing around in random directions at room temperature, colliding with its neighbors, moving constantly. The water looks uniform, same throughout. No particular pattern, no organization. To the eye, it might seem like a high-entropy, disordered state. And it is. But the crucial point is that the number of ways you could rearrange the molecules of that glass of water while keeping it looking like a uniform glass of water is still inconceivably large. Now consider DNA. The DNA in a single human cell is a sequence of about 3 billion base pairs. That sequence is highly specific. Change any significant portion of it and the molecule no longer works, no longer encodes functioning proteins, no longer does what it is supposed to do. From an entropy standpoint, a working DNA molecule is an extraordinarily low entropy object. The number of base pair sequences that produce a functional genome is vanishingly small compared to the number of random sequences you could build from the same components. But DNA does not look especially ordered. It is a twisted spiral in solution. It is not visually impressive the way a crystal is visually impressive. This is the trap. Entropy is about information, not appearance. It is about how constrained the system is. How few of all the possible arrangements are actually compatible with the system being what it is and doing what it does. Living things are extraordinarily low entropy in this informational sense. Not because they look neat. Because the fraction of all possible molecular arrangements that would produce a functioning organism is incomprehensibly small. A bacterium is not just a specific arrangement of atoms. It is one of a tiny subset of arrangements that maintains itself, replicates, responds to its environment, and does all the remarkable things that living things do. And this is exactly why life is so remarkable from a thermodynamic standpoint. Not because it defies the second law. It absolutely does not. But because it represents a degree of informational organization that should be extraordinarily rare. And yet here it is, covering an entire planet, having persisted for nearly 4 billion years. How? That is the question that sits at the heart of this story. The arrow of time. There is a consequence of the second law that most physics textbooks mention and most readers pass over too quickly to feel the full weight of. The second law of thermodynamics is the reason time has a direction. This statement sounds philosophical. It is not. It is a precise physical claim. The fundamental laws of physics, Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, quantum mechanics, are all symmetric in time. Run any of their equations backward and you get valid physics. A film of 2 billiard balls colliding plays perfectly physically whether you show it forward or in reverse. A film of a planet orbiting the sun looks equally legitimate in either direction. At the level of fundamental particle interactions, there is no arrow, no preferred direction, no physical difference between forward and backward, and yet time as we experience it runs in one direction only. The past is fixed and the future is open. You remember yesterday, but not tomorrow. Broken glasses do not reassemble, the dead do not return. Heat flows from hot to cold, never the reverse. The second law is the only fundamental law of physics that distinguishes past from future. It is the only law that treats the two directions of time differently. And it does so not because it is built into the fundamental equations of motion. It is not. but because of the specific initial conditions of the universe. Here is what this means. Imagine a film of a glass of water falling off a table, shattering on the floor, and the water splashing outward in all directions. You immediately recognize which direction time is running. Forward, glass falls, shatters, water spreads. Reverse, water contracts from the floor, glass shards leap upward, reassemble into a perfect glass, leap onto the table. The reverse film is recognizable as impossible not because it violates any conservation law, not because the energy accounting is wrong, but because it requires an extraordinary decrease in entropy. The scattered shards and spread water contain vastly more entropy than the intact glass on the table. Getting from scattered to intact requires a spontaneous entropy decrease of extraordinary magnitude, which the statistical mechanics of large systems essentially never produces. The arrow of time is the arrow of entropy. Time flows forward because entropy increases in what we call the forward direction. And that direction became the forward direction because the universe started in an extraordinarily low entropy state. If the universe started in a high entropy state, if it began in maximum disorder, as you might naively expect of a beginning that emerged from nothing, entropy could not increase. Because you cannot increase what is already maximum, there would be no arrow of time. Events would be equally likely in either direction. There would be no past and no future, just a static maximum entropy equilibrium in which nothing of interest could happen. The fact that time has a direction, the fact that you remember yesterday and not tomorrow, that causes precede effects, that broken glasses stay broken, is evidence that the universe began in a state of extraordinarily low entropy. That is one of the deepest facts about reality. And it raises immediately, almost violently, the question of why. The low entropy beginning. The universe started hot, dense, and, here is the crucial and counterintuitive part, remarkably smooth. In the first fractions of a second after the Big Bang, matter and energy were distributed through space with extraordinary uniformity. The temperature was the same everywhere to within tiny fractions of a percent. The density was the same everywhere to a similar precision. The universe was, in its early state, astonishingly homogeneous. This sounds like it should be a high entropy state. Uniform, featureless, everything evenly distributed. Isn't that what maximum disorder looks like? For ordinary gases in a box, yes. A gas reaches maximum entropy when it fills the volume uniformly, because that is when the molecules have the most ways to be arranged while still producing the same macroscopic appearance. But gravity changes everything. In a gravitating system, the high entropy state is not uniform. It is clumped, it is concentrated, it is matter collapsed into the most compact configurations gravity can produce. For a gravitating system, the maximum entropy state is everything collapsed into black holes. This is a profound and initially deeply counterintuitive result. In a universe dominated by gravity, which is our universe, smooth and uniform is low entropy. Clumped and concentrated is high entropy. The early universe, with its extraordinary smoothness, was in an extraordinarily low entropy state, not despite appearing simple and uniform, but precisely because of it. The universe began with entropy far from its maximum. And since then, for 13.8 billion years, it has been doing exactly what the second law predicts. It has been moving toward higher entropy. Matter has clumped under gravity, stars have formed. Those stars have burned their nuclear fuel, converting the low-entropy potential energy of nuclear forces into the higher entropy thermal energy of radiation. Galaxies have formed structures. Black holes have grown. The universe has been, in the most literal thermodynamic sense, running down. And it will continue to run down. For timescales that make the current age of the universe look like a preliminary sketch, it will continue moving toward maximum entropy, toward what physicists call the heat death, the final state of maximum disorder, uniform temperature, no gradients, no structure, nothing interesting left to happen. But here, at the bottom of the entropy story, the deepest question arrives. Why did the universe start in such a low entropy state? The second law tells us entropy increases. It does not tell us why entropy was low to begin with. It does not tell us why the Big Bang produced the specific, extraordinarily unlikely initial conditions that set entropy on its long upward trajectory. It takes the initial state as given and then describes what happens next. What set the initial state is a question that the second law cannot answer. It is a question that currently no other part of physics can answer either. The Boltzmann brain problem. Before Ludwig Boltzmann died in 1906, he took his own life in a hotel room in Duino, Italy, partly from depression exacerbated by the decades of resistance his ideas had faced. He had already grasped the deepest implication of his own work. If entropy tends to increase, then the current state of the universe, with all its galaxies and stars and planets and biological complexity, represents an extraordinarily improbable state, far from the equilibrium that the second law drives everything toward. One way to produce this improbable state is exactly what the Big Bang scenario proposes. The universe started in a specific, extraordinarily low entropy initial condition and has been evolving upward through entropy ever since, with the ordered structures we see around us representing the kinds of complexity that can temporarily emerge on the way from very low entropy to maximum entropy. But there is another way to produce an improbable low entropy fluctuation, purely by chance, in a universe that had somehow reached maximum entropy. In the heat death, in the long, cold, featureless equilibrium of the very far future, quantum fluctuations would continue to occur. The vacuum is never truly static. Virtual particles appear and disappear. Quantum fields fluctuate, and in a universe with infinite time available, those fluctuations would, with absolute statistical certainty, eventually produce every possible configuration of matter, no matter how improbable. Given infinite time, a quantum fluctuation would eventually produce a galaxy, a solar system, a planet, a single cell, a human brain, fully formed, complete with memories of a past that never happened, existing for a moment before dissolving back into the equilibrium. This hypothetical, spontaneously fluctuating brain is called a Boltzmann brain. And it is not merely a philosophical curiosity. Here is why it matters. If the universe is enormously old or infinitely old, Boltzmann brains would be produced in unimaginable numbers. In fact, they would be produced far more frequently than brains like ours. Brains that emerge through billions of years of stellar evolution and biological evolution and civilizational development from a specific low-entropy Big Bang. If Boltzmann brains vastly outnumber ordinary brains, then in any random sample of observers in the universe, the overwhelming majority would be Boltzmann brains, which means any given observer, you sitting there reading this, is overwhelmingly more likely to be a Boltzmann brain than an ordinary, evolved brain. But Boltzmann brains would have false memories. They would remember a past that did not happen. They would find themselves existing in an otherwise empty universe. They would have experiences that, on close examination, would not be consistent with what a reliable cognitive apparatus built by evolution would produce. If you are a Boltzmann brain, your memories of reading previous words in this sentence are false. Your confidence that you exist in a universe with a consistent history is unwarranted. Your belief that physics works reliably is itself random fluctuation. This is the Boltzmann brain problem. Any cosmological model that predicts the universe is sufficiently old and sufficiently large to produce Boltzmann brains in overwhelming numbers faces a devastating self-undermining conclusion. The observers that model produces would mostly be unreliable, and if observers are mostly unreliable, the physics those observers developed cannot be trusted, including the physics that led to the model. The problem is not merely philosophical. It is a genuine constraint on cosmological theories. A theory of the universe that produces too many Boltzmann brains is, in a precise sense, self-defeating. Modern cosmological models, including those based on eternal inflation, are actively wrestling with this problem. It has not been solved. It is, in the opinion of some very serious cosmologists, the single deepest unsolved problem in the foundations of physics. Stars as entropy engines. Now step back from the abstract and look at the universe as it actually is. The universe has been increasing in entropy for 13.8 billion years. The second law has been relentlessly driving everything toward greater disorder. And yet, instead of looking like a featureless soup of maximum entropy, the observable universe is filled with extraordinary structures. Galaxies, stars, planets, life. How? How can the universe be both moving toward maximum entropy and simultaneously producing structures of breathtaking complexity? The answer is that entropy does not increase uniformly everywhere at the same rate. It increases on average across the whole system. But locally, in specific regions, entropy can decrease, as long as the entropy of the surrounding environment increases by a larger amount. This is not a violation of the second law. It is a consequence of it. The overall entropy of the universe increases. Local pockets of decreasing entropy are paid for, always, by larger increases elsewhere. Stars are the clearest example of this mechanism in operation. A star is an entropy engine. It takes the concentrated gravitational potential energy of a collapsing cloud of gas, a relatively low entropy state, because the cloud has one specific property: it has not yet collapsed, and converts it into nuclear energy, radiation, and heat. The nuclear fusion in a stellar core converts the low-entropy potential energy of hydrogen into the slightly higher entropy product of helium, releasing energy in the process. That energy flows outward through the star, reaches the surface, and radiates into the surrounding space as photons. The photons spread outward in all directions, carrying entropy with them, distributing energy across an ever larger volume of space. Here is the key detail. The star takes in photons from its own nuclear reactions, concentrated, high-energy photons, and emits many lower-energy photons in return. The total energy is conserved, but many low-energy photons represent more entropy than fewer high-energy photons carrying the same total energy. The star is a machine for converting low entropy concentrated energy into high entropy, dispersed energy. And in the process of doing this, in the flow of energy from stellar interior to stellar surface, something extraordinary becomes possible. Temperature gradients. Energy flowing down a temperature gradient, from hot to cold, from stellar interior to space, is energy capable of doing work. And where energy can do work, complexity can emerge. Chemistry can happen. Chemical reactions can build complex molecules. Complex molecules can encode information. Information encoding molecules can replicate. Replicating molecules can evolve. Every form of complexity in the observable universe, including you, exists in the flow of energy from hot stars to cold space. Life is not a violation of the second law. Life is a thermodynamic process, a highly efficient and extraordinarily sophisticated entropy-generating machine that happens, as a byproduct of its entropy-generating activity, to be aware of itself and curious about the laws it is subject to. The philosopher Erich Schneider and the biologist Dorian Sagan put it memorably. Life doesn't go against the second law. Life is the second law in action. The biosphere increases entropy faster than a lifeless Earth would. Life is, from a thermodynamic perspective, the universe's way of burning through its low entropy initial conditions as efficiently as possible. Whether this is comforting or alarming is a matter of temperament. The discovery that changed everything. In 1998, two independent teams of astronomers were doing something that should have been straightforward. They were measuring the brightness of distant supernovae, specifically Type I supernovae, thermonuclear explosions of white dwarf stars that are useful as distance markers because their intrinsic brightness is known. By measuring how bright they appear from Earth, you can calculate how far away they are. The two teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were using this technique to measure how the universe's expansion rate had changed over time. Everyone expected to find that the expansion was slowing down. Gravity should be putting the brakes on. All that matter pulling on all that other matter should be decelerating the expansion that began with the Big Bang. Instead, they found that the expansion was speeding up. The distant supernovae were dimmer than expected. They were farther away than a decelerating expansion would have placed them. The universe was not slowing down. It was accelerating. Something was pushing space apart, overcoming gravity, driving the expansion to go faster and faster. That something is called dark energy. It constitutes roughly 68% of the total energy content of the universe. Its nature is, as of today, completely unknown. The simplest explanation is that dark energy is a property of space itself, a fixed energy density that every cubic meter of empty space carries regardless of what else is in it. Einstein had actually included such a term in his field equations in 1917 and called it the cosmological constant. He added it for the wrong reasons. He was trying to produce a static universe before Hubble showed the universe was expanding, and he later called it his greatest blunder. It turns out it was not a blunder. The universe contains exactly the kind of term Einstein had speculatively introduced, but in an amount that he had not predicted. The cosmological constant has a value that is, in the context of quantum field theory, astonishing. Theoretical estimates of what the energy density of the vacuum should be, based on the quantum mechanical fluctuations of all the fields that permeate space, are roughly 10 to the power of 120 times larger than the measured value. This is the largest discrepancy between theoretical prediction and experimental measurement in the history of physics, by an enormous margin. It is so large that it is either a sign that we fundamentally misunderstand something about quantum field theory, or a sign that some extraordinary mechanism is cancelling almost all of the vacuum energy, leaving only a tiny residual. Nobody knows which. Nobody knows why the cosmological constant has the value it has. The problem has been called the worst prediction in the history of physics, and it has been sitting unresolved in the foundations of cosmology for decades. What we do know is the consequence. The accelerating expansion of the universe is taking it toward a specific thermodynamic fate that differs in detail from earlier predictions. As the expansion accelerates, the horizon of the observable universe, the boundary beyond which light cannot reach us because the expansion is carrying distant regions away faster than light, will shrink. Galaxies beyond our local group will eventually cross that horizon, disappearing from our observable universe forever. The observable region will grow emptier and emptier. Stars will burn out. The last red dwarf will exhaust its fuel in perhaps 100 trillion years. The universe will enter the dark era, then the degenerate era, as the remnants of dead stars slowly cool. Then the black hole era, as Hawking radiation slowly evaporates even the largest black holes over timescales measured in 10 to the 90 years and beyond. And then the dark era, the long, cold, featureless equilibrium of maximum entropy. Dark energy ensures that this equilibrium is not perfectly static. The accelerating expansion means the universe approaches a state called de Sitter space, a universe dominated by the cosmological constant, expanding exponentially, with a fixed horizon and a small but non-zero temperature associated with that horizon through the same mathematical mechanism that gives black holes Hawking radiation. In de Sitter space, thermal fluctuations never quite stop. The temperature is extraordinarily small, about 10 to the minus 30 Kelvin, far colder than anything that exists in the current universe. But it is not zero, and thermal fluctuations in a de Sitter universe that persists forever would, given infinite time, produce Boltzmann brains. Which brings us back to the problem we left unresolved in the previous section. Now, with the added complication that dark energy seems to be engineering the specific final state in which the Boltzmann brain problem is most acute. Maxwell's demon. In 1867, the same year Boltzmann was beginning his career in Vienna, a Scottish physicist named James Clerk, Maxwell invented one of the most famous thought experiments in the history of science. Maxwell imagined a container of gas divided into two chambers by a wall. In the wall, there was a tiny door operated by a tiny demon. Intelligent, fast, with perfect knowledge of the speed and direction of every gas molecule heading toward the door. The demon watches the molecules approach. When a fast-moving molecule approaches from the right chamber, the demon opens the door and lets it through to the left. When a slow-moving molecule approaches from the left chamber, the demon opens the door and lets it through to the right. Fast molecules accumulate on the left, slow molecules on the right. One side gets hotter and the other gets colder, without any work being done on the gas itself. This appears to violate the second law. The entropy of the gas has decreased, Order has been created from disorder, and the demon has done it without expending any energy on the gas. For nearly a century, Maxwell's demon was a genuine puzzle. It seemed to show that a sufficiently intelligent agent could sort molecules, decrease entropy, and effectively break the second law. The implications would be extraordinary. Free energy, perpetual motion, the ability to build order from disorder at will. The resolution came from an unlikely direction. In 1961, the physicist Rolf Landauer showed that the demon must keep a record of every measurement it makes. It must store information about which molecules are fast and which are slow. And eventually that memory must be erased, because the demon has only finite memory capacity and eventually fills it up. And erasing information has a thermodynamic cost. Each bit of information erased increases the entropy of the environment by a specific, calculable amount. The demon's sorting gains are exactly cancelled by the entropy cost of erasing its memory. The second law holds. The demon cannot win. This result, Landauer's principle, established something profound. Information is physical. Information is not an abstract mathematical concept that floats free of material reality. Information is instantiated in physical states. In the manipulation of information, its storage, processing, erasure, has thermodynamic consequences. It costs entropy to erase information. The act of forgetting generates heat. This is not a metaphor. This has been confirmed experimentally. In 2012, a team at the École Normale Supérieure in Lyon measured the energy cost of erasing a single bit of information stored in a colloidal particle trapped by a laser. The measurement agreed with Landauer's prediction to within experimental precision. Information is physical. Thinking has thermodynamic costs. Every computation you perform, every memory your brain consolidates, every thought that passes through your mind and is then forgotten, all of it generates entropy. Your mind is an entropy engine, more sophisticated than a star in some ways, simpler in others, but subject to the same law, the same inexorable preference of the universe for disorder over order. Maxwell's demon cannot beat the second law, but in trying to defeat it, it taught us something about the relationship between information and entropy that is still being worked out in quantum computing, in black hole physics, in the foundations of statistical mechanics. The demon lost, but the lesson it left behind is still being unpacked. Black holes and the entropy catastrophe. In 1972, a young graduate student at Princeton named Jacob Bekenstein made a suggestion that his supervisor, the legendary physicist John Wheeler, initially found implausible. Bekenstein suggested that black holes have entropy. This was not an obvious idea. Black holes, as understood at the time, seemed to be perfectly simple objects. They had mass, charge, and angular momentum, and nothing else. No internal structure, no complexity, no room for any of the microscopic configurations that entropy is supposed to count. A black hole was the simplest possible object in general relativity. The idea that such an object could have entropy seemed contradictory. But Bekenstein noticed a problem. If you threw a cup of hot coffee, a high-entropy object, into a black hole, the black hole would absorb the mass and grow slightly larger, but its simplicity would be unchanged. From outside the black hole, it would still appear to have only mass, charge, and angular momentum. The entropy of the coffee would simply have vanished. This violated the second law. You had decreased the entropy of the observable universe by hiding entropy inside a black hole. If black holes could swallow entropy without consequence, they were entropy sinks, machines for getting around the second law. Bekenstein proposed that black holes must have entropy proportional to the area of their event horizon, the boundary beyond which nothing, not even light, can escape. Not proportional to their volume, as you might naively expect for a three-dimensional object, but to their surface area. This proposal was initially controversial, but in 1974, Stephen Hawking made a calculation that transformed it from a clever suggestion into a startling physical result. Hawking showed that black holes are not perfectly black. Through a quantum mechanical process near the event horizon, where quantum fluctuations produce pairs of virtual particles, one falling into the black hole and one escaping as real radiation. Black holes emit a faint thermal glow. The temperature of this radiation is inversely proportional to the black hole's mass. Larger black holes are colder, smaller black holes are hotter. This Hawking radiation confirmed that black holes have temperature, which meant they have entropy, which meant Bekenstein was right. The entropy of a black hole is proportional to its event horizon area, measured in units of the Planck area. The Bekenstein-Hawking entropy formula revealed something extraordinary about the nature of entropy itself. For any other physical system, entropy scales with volume. Double the size of a gas, and the entropy roughly doubles. But for black holes, entropy scales with area, with the two-dimensional surface, not the three-dimensional interior. This is the holographic principle. The entropy, which measures the information content, of anything inside a black hole is not encoded in its volume, but on its surface. The information that describes the interior is somehow contained in the boundary. Juan Maldacena's 1997 ADS/CFT correspondence showed that this principle extends beyond black holes. A theory of gravity in a volume of space is equivalent to a theory with no gravity on the boundary of that volume. The physics of three dimensions can be completely encoded in two dimensions. Space may have fewer dimensions than it appears. This is not yet fully understood. The holographic principle sits at the frontier of theoretical physics, connecting quantum mechanics, gravity, information theory, and the nature of space itself. It may be one of the most important ideas in the history of physics, or it may be a technical result specific to particular kinds of space-time geometries. Nobody is sure. But black holes and entropy have done this before. They have a habit of pointing towards something deeper. Life as thermodynamic defiance. Here is the central paradox that all of this has been building toward. The universe prefers chaos. The second law is absolute. Entropy increases, always and everywhere, in the net. The universe began in an extraordinarily improbable low-entropy state and has been moving toward maximum entropy for 13.8 billion years. And in that movement, in the long fall from order to disorder, from structured to uniform, from concentrated to dispersed, the universe has produced chemistry and biology and consciousness. It has produced things that know the second law and are troubled by its implications. This is deeply strange if you think about it. The second law does not predict that the route from low to high entropy should be interesting. It predicts the opposite. Given any initial configuration, the most probable evolution is direct and rapid movement toward the highest available entropy. Interesting complexity. Structures that are neither at maximum entropy nor at the initial minimum entropy, but somewhere in the rich middle, requires specific conditions. It requires the right thermodynamic gradients, the right timescales, the right chemistry. Life, in particular, is an extraordinary thermodynamic phenomenon. Living things maintain their internal order by continuously processing low-entropy inputs, food, sunlight, and exporting high-entropy outputs, heat, waste. A living cell is not a static low-entropy structure. It is a dynamic, constantly driven, continuously maintained low-entropy structure. The moment the driving stops, the moment the organism can no longer process energy, entropy wins immediately and completely. Death is the second law reasserting its preference. But while life operates, it is one of the most efficient entropy-producing processes in nature. Studies of the thermodynamics of evolution suggest that organisms that are better at capturing energy gradients and converting them to entropy are, in many environments, fitter than those that are less efficient. Natural selection may, in the right conditions, favor organisms that are better at running down the universe's low-entropy reserves. If this is correct, then evolution is not just a process operating within thermodynamic constraints. It may be a process that is partly driven by thermodynamic gradients. Life emerges and diversifies because it is thermodynamically favored, not in the naive sense that it decreases entropy locally, but in the precise sense that it increases the total rate of entropy production more effectively than the alternatives. The universe prefers chaos. But the most effective path from order to chaos in the specific physical conditions of a planet near a star with access to complex chemistry turns out to run through life. This does not make life inevitable. It does not predict that any given planet will develop biology. It does not replace evolution or natural selection. It is a thermodynamic framework within which evolution occurs, not a replacement for it. But it does suggest something remarkable. The existence of life may not be a miraculous accident that defies the laws of physics. It may be, in a very specific sense, the laws of physics working as they always do. Entropy increasing, the universe doing what it always does. The route it takes this time happening to run through something that can write a script about why it exists. The fate written in entropy. Let us now follow the second law to its logical conclusion. Past the present, past the end of stars, into the deep future. In roughly 5 billion years, the Sun will exhaust the hydrogen in its core. Nuclear fusion will cease. The outward pressure that has balanced gravity for 10 billion years will vanish. The Sun will expand into a red giant, its outer layers swelling to swallow Mercury, Venus, and possibly Earth. The core will contract into a white dwarf, a dense, slowly cooling sphere of carbon and oxygen, roughly Earth-sized, 1,000,000 times denser than water, held up by the quantum mechanical pressure of its own electrons. The white dwarf will cool. For billions upon billions of years, it will radiate away its stored thermal energy into the surrounding space. Slowly, it will dim from white to yellow to orange to red to the deep infrared that no eye could detect. Eventually, after timescales that dwarf the current age of the universe, it will become a black dwarf, a cold, dark, inert ball of crystal floating in the dark. No black dwarfs yet exist. The universe is not old enough. The oldest white dwarfs, the remnants of the first generation of stars, have been cooling for billions of years but have not yet reached the temperature threshold. Every black dwarf in the future universe is a thermodynamic fossil, a record of a star that once burned, that was once a pocket of intense order fighting against entropy, that eventually lost the fight and cooled to equilibrium. The more massive stars end differently. They exhaust their fuel faster, burn through heavier and heavier elements in a sequence of fusion stages, and ultimately collapse. If the collapsing core is massive enough, gravity overwhelms even neutron degeneracy pressure, and the core collapses into a black hole, a region of space-time so severely curved that not even light can escape from within the event horizon. Black holes are the universe's highest entropy objects. Their Bekenstein-Hawking entropy is enormous. A stellar mass black hole has entropy of roughly 10 to the 77 in units of Boltzmann's constant. A supermassive black hole at the center of a large galaxy has entropy measured in units of 10 to the 90 or beyond. Black holes are entropy sinks. They swallow ordered structures and increase the universe's total entropy in enormous single steps. But black holes are not eternal. Hawking radiation. A black hole radiates energy at a temperature inversely proportional to its mass. As it radiates, it loses mass. As it loses mass, it gets hotter. As it gets hotter, it radiates faster. A stellar mass black hole takes roughly 10 to the 67 years to evaporate. A supermassive black hole with billions of solar masses takes roughly 10 to the 93 years. These numbers have no human meaning, but they are finite. Every black hole will eventually evaporate. Every structure the universe has produced, every galaxy, every star, every planet, every living thing, will either fall into a black hole or decay. And every black hole will eventually evaporate into Hawking radiation. What is left? A universe of thermal radiation, photons, electrons, positrons, neutrinos. Nothing bound together. No atoms. If protons decay, as many extensions of the Standard Model predict on timescales of roughly 10 to the 36 years, then even the white dwarfs and neutron stars dissolve. Every proton in every nucleus eventually converting into lighter particles through spontaneous quantum processes. Everything that has ever existed is reduced to its lowest energy components, dispersed as uniformly as the expansion of space allows, at a temperature approaching but never quite reaching absolute zero. Maximum entropy, thermal equilibrium, no gradients, no structure, no complexity, nothing interesting left to happen. The heat death, the thermodynamic end of everything, except in a de Sitter universe with a positive cosmological constant, even this equilibrium has a temperature, an extraordinarily small one, 10 to the minus 30 Kelvin, but not zero. Thermal fluctuations never fully stop. And given infinite time, those fluctuations produce structure, random structure, fleeting structure, Boltzmann brains and Boltzmann galaxies and Boltzmann universes, each one lasting a moment before dissolving back into the equilibrium from which it randomly emerged. This is where the second law runs out. Not because entropy stops increasing. It does not. But because in the very far future, in the de Sitter equilibrium, the distinction between increasing and decreasing entropy becomes almost meaningless. Fluctuations go both ways. Order and disorder alternate randomly, with the distribution of states following quantum statistical mechanics. The universe reaches a state where the second law is always satisfied on average, but locally, fleetingly, randomly violated in both directions simultaneously. The thermodynamic story ends not with a clean conclusion, but with an uncomfortable stochastic blur. The universe prefers chaos. In the end, it achieves it. And then it begins again, spontaneously, at random, for no reason, because there is nothing left to prevent it. What we do not know. The honest account of entropy and the universe's preference for disorder has a long list of genuinely open questions, and they deserve to be stated clearly. We do not know why the universe started in a low-entropy state. The Big Bang's extraordinary smoothness and the corresponding low initial entropy are among the most important and least explained facts in cosmology. The Penrose argument, named for the physicist Roger Penrose, who calculated that the initial entropy of the universe is incredibly far from maximum, shows just how extraordinary the beginning must have been. But the mechanism that produced those initial conditions is unknown. Inflation can explain the flatness and homogeneity, but not the initial low entropy from which inflation itself began. Something set the initial conditions. We do not know what. We do not know the physical nature of dark energy. The accelerating expansion it drives changes the long-term thermodynamic fate of the universe in ways that matter enormously for the Boltzmann brain problem and the ultimate fate of structure. Understanding what dark energy is, whether it is a cosmological constant, a dynamic field, or something else entirely, is one of the primary goals of observational cosmology for the coming decades. We do not know whether protons decay. If they do, the timeline for the dissolution of ordinary matter is set. If they do not, white dwarfs and neutron stars might persist for essentially arbitrary timescales, changing the entropy budget of the very far future. Experiments running in underground detectors have not found proton decay. The simplest grand unified theories are ruled out. More complex theories with longer proton lifetimes remain untested. We do not know whether Hawking radiation is real in the full physical sense. It has not been directly observed. The temperature of Hawking radiation from any known black hole is far too small to detect against the cosmic microwave background. The theoretical argument for it is extremely compelling and is accepted by the vast majority of physicists. But direct experimental confirmation does not yet exist. We do not know the resolution of the Boltzmann brain problem. Cosmological models that produce de Sitter space in the far future appear to generate vast numbers of Boltzmann brains, undermining the reliability of the observers those models contain. Several proposed solutions exist: eternal recurrence, cyclical cosmologies, the no-boundary proposal of Hartley and Hawking, specific measures over the inflationary landscape. But none commands universal agreement, and none is confirmed. And we do not know, at the deepest level, why there is a second law at all. The statistical argument explains why entropy tends to increase given that the initial state has low entropy. It does not explain why entropy must always increase. It does not rule out the possibility of spontaneous entropy decreases. It says they are extraordinarily improbable, but improbable is not impossible. Whether the second law is a statistical tendency or a genuine constraint imposed by the structure of reality, whether it is a law in the same sense that conservation of energy is a law, or a very reliable approximation that breaks down at extreme timescales, is a question that remains philosophically unresolved. The second law has never been violated in any experiment ever performed. That record is one of the most impressive in science. But the theoretical foundations of that record are less airtight than the empirical record suggests. The pocket of order. Ludwig Boltzmann died in 1906 without winning the argument he had spent his career making. His statistical interpretation of thermodynamics, his proof that entropy is a count of microscopic possibilities, was not accepted by the physics establishment during his lifetime. The atomic theory of matter that underpinned it was actively disputed by influential colleagues. The man who identified one of the most fundamental laws of nature was, at the end, isolated, ill, and unconvinced that his legacy would survive him. Within 2 years of his death, Einstein's analysis of Brownian motion had confirmed the atomic theory beyond reasonable dispute. Within a decade, Boltzmann's statistical mechanics had become the foundation of a new field. Within a generation, quantum statistical mechanics had extended his work to the microscopic regime. His equation was engraved on his tombstone. The physics establishment does not always recognize its most important contributions in time. What Boltzmann found, and what we have been following throughout this entire script, is a law that governs everything, from the cooling of coffee to the expansion of the universe, from the direction of time to the existence of life, from the structure of black holes to the ultimate fate of every atom that has ever existed. The universe prefers chaos over order, not because chaos is better or more beautiful or more natural in any deep metaphysical sense. It prefers chaos because there are more ways to be chaotic than to be ordered, because probability, applied at the scale of 10 to the 80 particles interacting over 13.8 billion years, is as close to an absolute law as anything in physics. And yet, here you are. A temporary, improbable, thermodynamically maintained pocket of order, reading these words, thinking these thoughts, in defiance of, or rather in service of, the universe's overwhelming preference for the alternative. You exist in the gap between the universe's extraordinarily improbable beginning and its maximally entropic end. In the long fall from order to chaos, in the specific region of that fall where the gradients are right and the chemistry is possible and the time scales are long enough for biology to have emerged, you are the universe becoming briefly aware of the law that will eventually undo everything it has made. Now, I asked you at the start to look around and tell me whether your space is tidy or messy. Here's what I actually want to know now. After everything in this video, after entropy and Boltzmann brains and the heat death and Hawking radiation and the 10 to the 120 discrepancy and Maxwell's demon, does it change anything for you? Does knowing that the universe systematically, statistically, irreversibly prefers chaos make the order around you seem more precious or more pointless? Drop your answer in the comments. Tell me whether the room around you is tidy or chaotic, what time of day it is, and whether what you just heard feels like a liberation or a weight. I want to see how many different pockets of temporary order in how many different corners of this improbable planet are sitting with the same question at the same time. The universe will eventually reach equilibrium. It has not reached it yet. You are the proof. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.